Hello everyone. In this lecture, we'll discuss about the gate problems in three-phase induction motor. First one, when the supply voltage to an induction motor is reduced by 10%. Okay, the supply voltage is reduced by 10%. The maximum torque will decrease approximately. So, as the supply voltage is reduced, the torque will also get reduced. That is the maximum torque. So, we have to find out how much percentage the maximum torque will get decreased. So the options given are 5%, 10%, 20%, and 40%. So we all know the formula for the maximum torque is given by K into E2 square divided by 2x2. Okay. So in the first case, it is given that E2 is considered to its 100%. Okay. So we will consider K divided by 2x2 as a constant term K1 into E2 square. So this is the maximum torque in first case. So now in the second case, this E2 is reduced by 10%. So the available value of E2 will be 100 minus 10, that will be 90%. Only 90% of the supply voltage is available for us to calculate the maximum torque in the second case. So it can be written as K1 into 90% means 90 by 100 will be 0.9. So 0.9 times E2 is available. Okay. So it is reduced by 10%. So on simplification, we will get 0.9 square is 0.81 K1 into E2 square. So this is second equation. So by comparing these two equations, we can write Tm2 as 0.81 into Tm1 because K1 into E2 square can be written as Tm1. Okay. So in the second case, the maximum torque available is equal to 0.81 times Tm1. That is 81% of the maximum torque is available. Okay, only 81% is available. If we consider the first case as 100%, in the second case, it is available of about 81% of the maximum torque in first case. So, if we subtract 81 from 100, the remaining will be 19%. But in the option we have 20. So this will be approximately equal to 20%. So the answer is C. Next we'll solve the second problem. The second one is an induction motor having a full load torque of 60 Newton meter. When delta connected develops a starting torque of 120 Newton meter. Okay. So full load torque is given 60 Newton meter and starting torque is 120 Newton meter when it is delta connected. Okay. For the same supply voltage, if the motor is changed to star connection, so now the connection is changed to star, the starting torque developed will be. So we have to find out the starting torque. So the options are 40 Newton meter, 60 Newton meter, 90 Newton meter and 120 Newton meter. So during starting, a slip is equal to 1. So the starting torque can be written as K into R2 into E2 square divided by R2 square plus X2 square. So this is a formula for starting torque. So if we take the first case, in the case of a delta connected winding, this starting torque is given as 120 Newton meter. Okay. So this is for delta connected supply. So if the connection is changed to star connection, okay, in the case of a delta connection, we all know VL is equal to V phase. Whereas in the case of a star connected network, VL is equal to root 3 times V phase. Okay. Here, E2 is approximately equal to the supply voltage. Here we have to take the per phase value because all these values R2, X2 are the per phase values. So we have to substitute phase value over here. So this E2 can be written as VL divided by root 3 or E2 divided by root 3. So in the second case, when the supply connection is, when the winding is changed to star connection, this can be written as K into R2 into E2 divided by root 3 whole square divided by R2 square plus X2 square. So on rearranging this equation, we'll get 1 by 3 into K into R2 into E2 square divided by R2 square plus X2 square. Okay. So this is nothing but the torque, starting torque in the first case. This is TST1. So TST1 is given, which is 120. So 120 divided by 3 will be equal to 40 Newton meter. So when the connection is changed to star, the starting torque will get reduced to 40 Newton meter. So the answer is 40. Now we'll solve the third question. An 8-pole 3-phase 50 Hz induction motor is operating at a speed of 700 RPM. Okay, speed is given. The frequency of the rotor of the motor in Hertz is dash. So we have to find out the rotor current frequency, which is FR. Okay, so this is a straightforward question. We can solve it easily. Now we'll write the given data. Number of poles P is equal to 8. The supply frequency F is equal to 50. And the speed of the motor is 700 RPM. Okay, this is 50 Hertz. Now FR is equal to, the formula is S into FR. So where S is a slip is given by Ns minus N divided by Ns, where Ns is a synchronous speed. So Ns is equal to 120 F by P. So 120 into 50 divided by 8. So this will be equal to 750 RPM. So now substituting in S formula, we'll get S is equal to 750 minus 700 divided by 750. So this will be equal to 0.667. So now substituting in FR formula, FR is equal to S times F. So 0.0667 into 50. So this will be equal to 3.33 Hertz. So this is the answer. So now the fourth one is a 4-pole induction motor is working as an induction generator. Okay. So if a motor is working as an induction generator, then the slip will be negative. Okay. So the generator supply frequency is 50 Hertz. Supply frequency is given. The rotor current frequency is 5 Hertz. So the rotor current frequency FR is also given. The mechanical speed of the rotor in RPM. So we have to find out the speed of the rotor. Okay. So the options are 1350, 1650, 1950 and 2250. So first we'll write the given data. So the number of poles P is equal to 4. So it is working as an induction generator. So slip will be negative. And the supply frequency F is equal to 60 Hertz in this case. And then the rotor current frequency. So that is nothing but FR. FR is equal to 5 Hertz. So we have to find out the speed of the rotor. Okay, this is again a straightforward question only. So now N is equal to 1 minus S into Ns. So this is for the induction motor when it is running as an induction motor. So now when it is running as a generator, we have to replace S by minus S. Okay. So 1 minus of S will be equal to 1 plus S into Ns. So this is for the generator. Okay. So now we have to find S and Ns. So Ns is the synchronous speed. 120 into F by P. So 120 into 60 divided by 4. So this will be equal to 1800 RPM. Okay. So next we have to find out the slip. So FR is equal to S times F. Okay. So from this expression we can find out S. So FR by F. So 5 divided by 60, which is equal to 0.0833. Okay, this is the slip. So now we'll substitute in the N equation. N is equal to 1 plus 0.0833 multiplied by 1800. So this will be equal to 1949.94, which is approximately equal to 1950 RPM. So this is the answer. So the option C. Next, we'll solve the fifth question. The question is power input to a 500 volts, 50 Hertz, 6-pole, 3-phase induction motor running at 975 RPM is 40 kilowatts. Okay, input power is given. The total stator losses are 1 kilowatt. This is the stator losses. Next, the total friction and windage losses are 2.025 kilowatts. Then the efficiency is dash percentage. So we have to find out the efficiency of the induction motor. So now the formula for efficiency is power output divided by power input into 100. Okay, percentage efficiency. Okay. So now the input power is given. So first we'll write the given data. So input power of the motor is given, which is 40 kilowatts. Okay. So next the stator losses are given. Okay, stator losses are nothing but stator copper loss and stator core loss. So that is 1 kilowatts. So next, friction and windage losses are given. So friction and windage losses are nothing but the mechanical losses, which is equal to 2.025 kilowatts. Okay. So now, then the number of poles given, the supply frequency F is given, and the rated voltage, okay, of the motor is also given. So now we have to find out the output power. Okay. So if you take the induction motor, we are going to give a three-phase AC supply to the stator. Okay. So here input supplies, input power is given to the stator. So once the input power is given, this power has to supply the stator losses. Okay. So the stator losses includes both stator core loss and stator copper loss. So the output of the stator, which is nothing but the P2, power P2. So this is given as input to the rotor. Okay. So P2 is the output power of stator or input power of the rotor. So this P2 has to supply the rotor losses. So rotor losses in general are rotor copper loss only, because the rotor core loss is negligible. So this is PC. So now the output of the rotor is the gross mechanical power developed in the rotor. Okay, this gross mechanical power developed is nothing but P2 minus PC. Okay, so after this, this PM has to supply the mechanical losses. So PM minus the mechanical losses will give you the output power of the induction motor. Okay, so this PM, gross mechanical power developed, has to supply the mechanical losses. So the PM minus the mechanical losses will give you the power output. Okay, so now the power output is nothing but PM minus mechanical losses. The mechanical losses are given. Okay, so you're given with mechanical losses. So here again, if you want to find out P2, Pin is given and stator losses are also given. So P2 can be written as input power minus the stator losses. Okay. So now we are not given with the rotor copper losses. Okay. So but we have to find out PC. So there is one relationship between P2, PC and PM. So which is nothing but 1 is to S is to 1 minus S. So this is the ratio form of relationship between P2, PC and PM. Okay. So if you want to find out PM provided with P2 value, so we can write P2 by PM is equal to 1 divided by 1 minus S. So on cross multiplication, we can write PM is equal to 1 minus S times P2. So from this expression, we can find out P2. Okay. Sorry, PM. So first we have to find out P2. P2 is nothing but the input power minus the stator losses. Once we have found out P2, by using this expression, we can find out PM. So once we have this PM, so we can easily find out this power output. Okay. So first we'll find out P2. P2 is equal to Pin minus stator losses. Okay. So Pin is given 40 kilowatts. Stator losses are 1 kilowatt. So 39 kilowatts. So P2 is 39 kilowatts. So next what we have to find out is PM. So PM is nothing but 1 minus S times P2. So for that we have to find out S. So S is the slip given by Ns minus N divided by Ns. Okay. So N is the speed of the motor which is given. N is equal to 975 RPM. So now we have to find out the Ns value. Ns is a synchronous speed, as we all know, 120 F by P. So 120 into 50 divided by 6. So this will be equal to 1000 RPM. Okay. So Ns is 1000. So from this we can find out S. So S is equal to Ns minus N divided by Ns. So 1000 minus 975 divided by 1000. So this will be equal to 0.025. Okay. So now we can substitute this S value and P2 value in the PM equation. So PM is nothing but 1 minus S into P2. So we'll continue here. So PM is equal to 1 minus S into P2. So 1 minus 0.025 multiplied by 39 kilowatts. Okay. So on simplification, we will get 38.025 kilowatts. Okay. So now we have found out PM. So after that, we can directly find out the output power, which is nothing but PM minus the mechanical losses. Mechanical losses are nothing but friction and windage losses, which are given 2.025 kilowatts. So PM is 38.025 kilowatts minus the mechanical losses are 2.025 kilowatts. So on simplification, we'll get 36 kilowatts. So now the efficiency is power output by power input. Power output is 36, power input is 40. Multiplied by 100 will get 90%. So this is the answer. It's a sixth question. The frequencies of stator and rotor currents flowing in a three-phase 8-pole induction motor are 40 Hz and 1 Hz respectively. So the frequencies of stator current and rotor currents are. So the frequency of the stator current is nothing but the supply frequency F, which is 40 Hz. And the frequency of the rotor current is nothing but Fr, which is equal to 1 Hz. So now we have to find out the motor speed in RPM. Okay. So now the speed of the motor is given by 1 minus S into Ns. Okay. So we have to find out S and Ns. So again the same formula, Ns is equal to 120 F by P. So 120 into 40 divided by number of poles P is equal to 8. 8. So this will be equal to 600 RPM. Okay. So now Fr is equal to S times F. So S is equal to Fr by F. So 1 divided by 40. So this is equal to 0.025. So the speed of the motor is 1 minus 0.025 multiplied by 600. So this will be equal to 585 RPM. So this is the answer.